stopping at 100 kilometers, right? And how far, it's traveling at, so the v of t. So the velocity right now when he sees the accident is 100 kilometers per hour. How far ahead is the accident? So you know that this distance is 80 meters. Correct. And it says something that's really important here. What constant deceleration is needed? Constant deceleration is needed. So what you do is you say the acceleration in terms of t is going to be equal to some constant. So what do you want to call that constant? C. So what's the velocity now? Ct plus some constant, correct? Because you have to put in a constant at the end when you integrate. And then what would the position function be? It's usually s of t. C over 2 t squared plus dt plus e. You also know that the velocity at time 0. What's the velocity at time 0? 100 kilometers an hour, exactly. What's the velocity at time stop? 0, exactly. Hold on a sec, I'll get the door in a second. What's the position at time 0? We'll say 0. And what's the position at time stop? 80. You use this information to fill in the blanks and solve the question. Okay, so it gives you the function f of x is equal to root 3 sine x plus 3 cosine x. You're trying to find out at what x values the tangent line is horizontal. So what do you have to take first? So you end up with, and you want to set it equal to 0. So you're doing 0 is equal to root 3 cosine x minus 3 sine x. Is that correct? So what do you now have? You need to solve for x is what you now have. The entire question, Neil and Thomas, revolves around what does x equal. So you could have 3 sine x is equal to root 3 cosine x. You could then do sine x over cosine x is equal to root 3 over 3. So that's the same thing as tangent x, correct? So you need to know, when does tangent x equal root 3 over 3? You need to know that. You can use triangles to figure that out. That equals when what is true? When x is equal to pi over 6, but it also repeats itself. And the key to this one, the last half point, is how often does it repeat itself? Every pi, because tangent is going to be positive in the first and the third quadrant. What happened with yours is you created an extra solution when you squared it. Fine. It's very hard to track that down. Fawn used a really cool method. She, right here, I've never seen someone do this. It's a great idea. She squared both sides and got, she ended up with 9. Oh, it's a 9, isn't it? Did you square it right?
No, I divided both sides.
Oh, you divided first and squared it. But she squared it and then used the sine squared plus cosine squared is equal to 1 and got it all in terms of sine. But what you ended up with was sine of x is equal to plus or minus 1/2. The false answer is the negative 1. Sine of negative 1 doesn't work in this case. The simple way to remember this, is this true? No. Is this true? Yes. You can create things that aren't true by squaring. You have to be very, very careful about that. This is what you can do. If two things are equal, the natural log, and I use natural log mainly because it's shorter than log, is equal to the natural log of b to the 4th. Correct? What can you do with that 4th power now because it's a log? Bring it to the front. ln y is equal to 4 ln of b. Now you can take the derivative of both sides quite nicely. What's the derivative of ln y with respect to x? 1 over y prime equals 4 times 1 over b times what? b prime, because b is some, in this case, f of x. B is some blob, is that 10 something, right? Yeah, so what are you isolating? You're trying to isolate y, so what does y prime equal? 4y times 1 over b times b prime, exactly. This is a lot easier to do in general. It can make it so that you can flatten out logarithms really nicely. Remember too, a few log rules. What is the log? This is just a new topic. What's the log of a over b equal to? Exactly. So what this allows you to do is up here. After you flattened it out, we used one of them because we brought the 4 to the front, right? But this is a fraction, right? So you could split it out and make them smaller. It's a lot easier to do a lot of small logarithm differentiation than it is to do product chain, quotient, quotient, like over and over and over again. It generally is a little clean. Is it still pretty ugly? Yes. The answer is pretty ugly, but I think it's much easier. So the first thing you want to do on that one, the square root, so you're integrating from what, 0 to 4? 0 to 4 of the absolute value of the square root of x minus 1. Yes, there's extra. What are you actually finding there? You need to graph it first to see what this looks like. Where does it cross the x-axis when x is equal to 1? And what does this look like? The square root of x minus 1?
It's the square root of x.
Is that right? What's the square root of when I plug in 0 for x? Can you ever do that? Can I plug in 0 for this? So this graph is not correct. What's wrong? Yeah, where does it hit? Yeah. So what does it look like? Looks like this. And then it's absolute value. So you went from 0 to what? 4. Let's say 4 is right here. It's not, it says x equals 4 right here. Let me get a different color. So if you plug in x equals 4 right here, the absolute value, what does that do? It flips over. Yes, so you're looking for this area right here. You see that? If you just took the integral from 0 to 4, what's the problem? It's going to subtract this. It's going to be the net change. So what do you have to do? This part of the function flipped over. Which part of the function is that? That's from 0 to 1. So what do you turn this into? The integral from 0 to 1 of what function? Negative the square root of x minus 1 dx. Because you flipped it over. It's negative to begin with, so when you make it negative, what does it do? Makes it positive. Plus what? The integral from 1 to 4 of just minus 1 dx. Multiplying by negative just flips those two. And then you do it out. This has a